Okay, so you're being recorded from now on. Please be aware. Okay, and I am sharing now my screen. Good. Let's make this disappear. Okay. All right. So welcome back to class. I hope everybody's going to join now, slowly but surely. If not, I hope everybody's watching the recording. So we were meant to do an in-person class today, but one of my students on Monday tested positive for COVID. So I thought it was irresponsible to kind of go to campus today and have an in-person class with you guys. I am vaccinated and I believe the entire class on Monday is as well, but it's like, you never know. We don't know enough about the virus to disregard the fact that there may be some viral shedding. I don't know. It's hard to say, but I'd rather be safe than sorry, and I'd rather be safe and keep you guys safe. So I think that makes a lot of sense. Hi, Manvid. Good seeing you again. All right, so let's dive right in. So we are doing today, and I'm just quickly gonna pull off the syllabus. We're doing today the first graded lab. So this is actually where you're really gonna earn some points. And this is actually quite central. So this will be the first time that you're doing autonomously alone some coding exercises. We will be having 3 graded labs, not the end of the world. It's the same scheme with the practice labs. There's some exercises, a little bit more practically inclined. So they're gonna ask you some things to do practically. The first one is rather boring, but the next ones are going to be more challenging. So each of these graded labs is worth 100 points. You have a total of 3. It's worth 300 points. So this will then essentially lead to the final overview and the final grade. So we are right now at module 7. So here's graded lab. This is due not on the 21st. This is due on, so since we, so that would be, today is the 21st, right? That would be the 27th. Okay, this being changed. So it is due next week on Wednesday, not on Sunday. Okay, and then we have, today we're going to be talking about the estimation of confidence intervals. Very sharp. We're talking about confidence intervals for population mean. We're going to talk about confidence intervals for a population in a proportional setting. And we'll also construct some confidence intervals. So this is very important because confidence intervals are really, they're basically a basis kind of reporting metric. So it's a range that is being shown virtually with all differences that you will find. So if you compare 2 populations, the difference between these 2 populations will always be reported as a mean difference and 95% confidence interval. Reason for that is because with the confidence interval at the very same time, you do not only see the variability of that difference, so it's a mark of variability, but it also allows for you to do hypothesis testing on the spot with a confidence interval. And that's obvious. You have 2 birds with 1 shot. With 1 range, you have 2 purposes fulfilled, and you avoid having to report an extra parameter, which is the so-called p-value. That essentially is the probability that this difference you're seeing is only by random chance, and you don't have to report the p-value, strictly spoken. You can skip the p-value, and many journals are actually supporting that and asking for that you drop the p-values and you only include the confidence intervals. So this is basically, this is why this is important in praxis. So, but let's get, in principle, let's get to what we're going to be discussing now. So we talked last time, we talked about sampling distributions, we talked about the central limit theorem, if you remember. That was actually the last, and so last time, it was not last time, it was 2 weeks ago, because last time we spoke about diagnostic applications of probabilities. I have this one in between because I think it becomes too population oriented and becomes a little too dry. But now we need to get into hypothesis testing, and that knowledge from module 5 is important for this purpose. So we have the central limit theorem, which essentially relates a sampling distribution of means to the population distribution. What does that mean? So we have a population distribution, we have a mean of a population, right? So if we look here, let me open this up. If we look at the distribution of cholesterol in the US population, we have a wide distribution, right? Because in a population, you have a lot of outliers as well. And these outliers just build wider tails, and there's more variability in the population. Makes sense, right? So if you are starting now to basically take 100 samples of each 1,000 people out of the population of 400 million in the US, you basically will get means for each of your samples. So you randomly draw samples and you get a mean for each sample. And we did that. You remember the Ames data, Ames, Iowa? The living room sizes or living space sizes. This is essentially what we're doing, right? So the sampling distribution of the means is essentially nothing else but the distribution of the means that are drawn from random samples from the population. So the mean of the population and the sampling distribution, so there's an X bar, the mean in the sample and in the sampling distribution, which is like this random number of samples that you have sampled, are identical. They are to be the same. They're not really the same because if you have one sample, obviously it's not going to be the same, right? But if you take 100 samples, the mean is going to get kind of closer to the population mean. And as we will hear later, the larger your sample is, the more likely the mean is closer to the population mean. These are all the dynamics that you will essentially see with populations and samples. Secondly, the standard deviation of the population is related to the standard deviation of the distribution of the sample means, meaning the standard error of the mean. And this is the variability in the sampling distribution of the means. This is the standard error of the mean, is related to the standard deviation of the population by the square root of n. So basically the standard deviation of the population, we said, is larger than the sampling distribution of the mean variability. So that's why the variability of the sampling distribution of the means essentially is being related to the standard deviation by a division by the square root of the n. So the sample size of the sample divides and lessens the standard deviation of the population to what becomes then the standard error of the mean. Oops, sorry. Okay, sorry, okay. Good. This being said, gets us to the third part of the central limit theorem, is when the n gets larger, the sample distribution of the mean becomes more normally distributed. The same is true for the individual scores. The larger the n, the more likely it is to normally distributed. And this is even more so true when you do sample means. Okay, so this was just a recap to get you back on the page. So it's basically, so the mean, oops, okay. So the mean of population and sample is identical. Secondly, the relationship between population standard deviation and population and standard error of the mean of the sampling distribution, variability of the sampling distribution is related to the square root of the n. Thirdly, the larger the n, the more likely the sample mean is identical to the population mean. And secondly to that, the larger the n, the more likely it is normally distributed. So, and now we're gonna go, now we're gonna dive back in. So this is not a point estimates. Point estimates, confidence levels, p-values, and hypothesis testing. So what is a point estimate? A point estimate is somewhere in the sample, you're quantifying something and you're estimating something that relates to the population. So if you're saying, I have a sample of 100 individuals and I want to estimate what the population mean is, and I do this by calculating the mean and the sample, your sample mean essentially becomes a point estimate. Based on your sample, you can then, based on the sample and the standard error of the mean that you calculate with a known standard deviation, you can calculate confidence intervals. And this will give you a confidence interval within which you, to a certain degree or to a certain probability, are certain that you have within that range the population mean. So it's all about estimating the population mean. That's what you want to do. Then you have the p-values, and the p-values is essentially your probability that you see a difference between your sample mean and the population mean by pure chance. So this is the easiest case, the set statistic, where you compare sample to a population. And this is what you do in hypothesis testing. You're basically determining by calculating p-values whether the difference you see between your sample mean and the population mean is random chance or it's a real difference. So this all is being discussed in open intersection 4.1 to 4.2. Then the t-distribution, which we also will discuss and we'll quickly talk about there, is in open intersection chapter 5. So we have seen this graph just a minute ago. Again, same thing. Sampling distribution differ from population distributions. Mean of the population and the mean of the sampling distributions are identical, particularly with large n's. Relationship between standard error of the mean, which is the variability of the sampling distribution of the means. The standard deviation is the square root of the n. And the sample size n increases, the standard error decreases arithmetically, right? Because we're dividing the standard deviation by the square root of the n, and it's more likely to be normally distributed. The same thing you can do, and this is new now, this wasn't on the old slide, the standard error of the proportion can also be calculated or estimated by knowing the probability. So the probability in that case is the proportion. So when you have, again, the diabetes example, you have a prevalence of diabetes in your population of 10%, your probability to pick from a sample of 100, a random diabetic, is basically 10%, right? So if you have 0.1 as a proportion, you multiply this by 1 minus 0.1, and you divide this by the sample size, the size in your sample, you get the standard error of the proportion mean. And this is called the normal approximation, as you remember from the binomial distribution section. So this is how you also can calculate the standard error using proportions. So this relationship we have talked about. So we are looking again at the distribution of the sampling mean, and again the center is the mu, which essentially is x bar in the sample. The standard error is basically the sigma, which again relates to a population divided by the sample n, and the square root of the sample n. So important at this point is the distinction between mu, which is the population mean, the x bar, which is the sample mean, and the sigma, which is the population standard deviation, and the s, which is essentially the standard deviation of the sample. And now, so now the confidence interval essentially, and this goes now in the direction I talked about before. So we have a point estimate of the mean. The mean means to estimate the population mean. And the point estimate is your best guess. This is one single number. You have a sample of 100 people. You calculate the mean of cholesterol, and your sample cholesterol is your estimate that this is the population mean. With 100 people, likely not true. So you have no idea how close your estimate is really to reality. So for that, you need an interval. And the interval basically increases your probability that you really make a correct decision. So your interval is essentially an interval estimate is an interval between two numbers. So it basically gives you a margin of error of your estimate. So and you know margins of errors. It's like we all have seen election polls or whatsoever. They all have a margin of error. It goes exactly in that direction, right? You have a sample. Based on your sample, you get an estimate. Your estimate may be true or maybe not true, and then you basically you have a margin of error based on your sample size. And based on that, you can estimate whether this is really reflecting the population's opinion or not, or the population mean or not. So now, as an example, Professor Waldron has put forward here a random sample of 309 infants. I think it's a study I think it's an R internal study. So I think the data is around there. So you have 309 infants with a sample mean birth weight of 190.6 ounces. You have a standard deviation of 18.2 ounces. So with the standard deviation, so the standard deviation allows for the calculation of the standard error of the mean, and then there are two differences. Either you know it from the population, the standard deviation, or you estimate it from the sample. The difference here is which test you're going to use. Because if you know it from the population, you can use set statistics. If you estimate it from the sample, you're basically using T statistics. This will become important later on when we talk about the T statistics, and we will get there in a couple of slides. So set statistics we talked about with the calculation of the set score. You remember? It's X minus X bar divided by the sigma. Gets you the set score. And the set score allows you to characterize the normal distribution in terms of percentiles. Below which threshold you have that part of the population that basically has a value smaller than that. So now when we are looking now at average birth weight, so what's the average birth weight of infants in the population? Well, based on our point estimate, our best guess would be 119.6, right? Out of 309 infants, well, it's probably not the worst of all estimates. So what is the 95% confidence interval on the average birth weight? So now we know the standard deviation, right? And the standard deviation relates to the sample mean in the way of the bell-shaped curve, right? So based on that, we could now quantify the 95% confidence interval with defining the 95% confidence interval as the range within which we are 95% confident that the population mean is being located in. And this is important that this definition is understood, because what you hear often, and I am speaking about vintaged, experienced scientists, come in with the wrong notion that this interval, that the confidence interval actually means that it contains 95% of all infants in the population, which is obvious, absolute rubbish. So it's really the probability with which you can say the average of the population is contained. This being said, you have now your set to basically use your known standard deviation, which you have here, to basically take your mean as the mean of the sample, and you assume this to be the population mean. And now you are essentially using minus 1.96 and plus 1.96 as your 95% confidence interval. Reason for this range is because, I meant to show you, beyond 1.96, this is exactly 2.5%. So 2.5% of your population is smaller than a set score of minus 1.96. Analogously, 2.5% are larger than plus 1.96. This in total gives you 5%. So 1 minus 5 is 95. So the entire area under this curve is 1. Minus 2.5 here is 97.5, minus more 2.5 is 95. So this in between here from minus 1.96 to plus 1.96 is essentially 95% probability. So your mean means to represent the population mean. Your sample size will make it more likely to be identical to the population mean. If the sample size is smaller, your 95% confidence interval is also going to be wider because the variability is going to be larger, right? The standard error of the mean is larger. So your standard error of the mean is now essentially the standard deviation that you use to employ the set scores. So you're characterizing the distribution of the sample means. So you have one sample mean and you're building around that the standard error of the mean, and you use this margin of error to calculate the 95% probability. So this is a 1.96 and a plus 1.96 set score multiplied with the standard deviation that now has become the standard error because you're interested in means rather than individual scores. Essentially allows you to get your 95% probability that you're capturing the population mean in this interval. Does that make sense? Are you with me so far? I think it's kind of intuitive, right? But I think it's important to kind of see the graphs and see this graphically mapped out, because it kind of gives you a better feeling, because you will see, if you read scientific literature, you will see a confidence interval. There's no way that you won't see the CI. And I think it's just important to understand what does that actually mean. So these, obviously, using the CI underlies a couple of assumptions. One is that the sample is considerably large, or that the sigma is known and is not estimated as the S from the sample. When we have an estimate and the sample is rather small, we're going to use a T distribution, which we're getting to in a few. What is shown here, David M. Lane. So this is nothing else but an online calculator. You can calculate confidence intervals easily online. You don't need to go online. You can do it in Excel and in R quite easily. You need the standard, you need the mean, you need the standard deviation, you need the standard error, you need the set of 1.96 is always the same for 2.5 on both sides. So if you want 5%, you basically get 2.5 with minus 1.96 and plus 1.96. But essentially, you can also use different CIs. If you're interested in something that is a little bit more confident, you get 99% CI. And logically, if you want to be more confident, what needs to happen to the interval? It needs to be wider. If you want to be less confident, and you want a 90% confidence interval, which you may find, it's going to get narrower because you're less confident. So less confident means smaller intervals. So essentially, these are the calculations how you do that. So you get a sample mean, you assume the sample mean is identical to the population mean, you do plus minus 1.96 multiplied by the standard error as the standard error representing the distribution of the sample means. That is like the 100 times 1,000 samples that you have drawn, or 309 samples for those infants. Basically allows you to quantify and characterize your distribution of the sample means. You can do any confidence intervals that you want. You can just also do a 68% confidence interval and multiply this by the respective set score. You can do the same story with continuous variable or with binary variables. If you do it with binary variables, you can also do hypothesis testing that way. It's not the cleanest way, but it is one way to do it. All right. Important again is the interpretation of confidence intervals. The 95% CI does not imply that 95% of the population lies in that limit. And it does not account for the bias in the point estimate, whatever that actually means. 95% CI does provide an interval within which we have 95% confidence we have the population mean, and it contains the true population mean in 19 out of 20 random samples. And what does that mean? Because if you were to compute random samples, and you make here 100 random samples, you essentially get with each sample, you get a certain confidence interval. Each of your samples has a certain confidence interval, and it will, in 5 out of 100 cases, it will not be containing the mean, because that's your random error. That's your p-value of 5%. This is not capturing the population. So the population mean is fixed. So if a population of 400 million in individuals in the US, you measure of each individual a cholesterol, and then you take 1,000 off, and 1,000 die within a day. I don't know how many US citizens die in a day. I think 1,000 sounds about right, I guess. The cholesterol, the mean will not change. So you would need a large decrease in the population that the mean will actually change. It will not change with small. So it is not a random variable, it is fixed. Therefore, it doesn't really have an error or variance, but it does have a standard deviation, because that's a fixed way of calculation. If we took a repeated sample and constructed 95% CI around every sample mean, 95% of these intervals would contain the true population mean, 5 would not. And this is what I've shown you here, this graph. And this is important to kind of keep that in mind. It's like you have an error, and this is all sample based. So these are these repeated samples that we have drawn that essentially make it easier for you to grasp what this probability actually implies. So, and now, so are there any questions with that so far? It's kind of intuitive again. So the $1 million question is now, is a 99% CI larger or smaller than a 95% CI? So if we are more confident that we're capturing the population mean, does the interval have to be larger or smaller? Larger, because it's a brighter range, right? If you're a basketball player, it's easier to hit a large basketball. Just as a comparison, which is maybe quite illustrative. Does the size of the CI increase? Does the confidence increase or decrease? So if the CI is getting wider, does the confidence increase or decrease? So it's kind of the same. It's kind of the same thing, right? It gets wider. It gets wider when the confidence gets larger. So when the N increases, does the 95% CI increase or decrease? Now your samples are getting larger. What happens now? So we have now a standard error of the mean multiplied by 1.96 gets you one bound, multiplied by minus 1.96 gets you the other bound. So this set multiplied by the standard error is calculated by the population standard deviation. The standard error is calculated the standard deviation divided by square root of the N, meaning that when the sample size gets larger, your numerator, the standard deviation, is divided by a larger number, meaning the standard error gets smaller. You multiply it with 1.96 from the set, and the set gets smaller. Which also is kind of goes more in the direction of the central limit theorem, because if your N increases, your sample is more likely closer to the population mean. Goes in the same direction. So the variability decreases and gets smaller. So what does the CI tell us about the variability of individual in the population? Nada. Nothing. Good. Okay. Estimating average birth weights. So we have a given sample of size N309 with a sample mean of 119.6, sample standard deviation 18.2. We compute a standard error of 1.04. We're multiplying this with 1.96. So this is a rather unconventional way to depict 95% confidence interval. I personally like a different way of doing that. And I will show you that now, because I would like for you to actually embrace my way rather than this way. No, not like this. So we have now Excel somehow. Okay. So the point is, when you are depicting it that way, you essentially get here, this is the CI, but it doesn't really tell you much, right? The most elegant way to depict it in my head, in my mind, would be the following. So you basically have a mean of 119.6. Now you have a CI, you have a set, and you have a SE. You have a S. Now you have a sigma. We're still on the set statistic world. Okay, so the sigma is now 18.2. What do I put it as here? Okay, so now that the N is, what did you say? The N is 309. N 309.
Professor, do you mind expanding the Excel sheet just to get a better view?
Yeah, that's actually a good idea. Thanks for suggesting that. I was going to zoom in a bit. That better? So, okay. So 119.6, a standard error. So we said the standard error is now standard deviation sigma divided by a square root of 309. Right? That gets us to 1.035. So the set is 1.96. And the CI is standard error multiplied by 1.96. Right? That's the 2.2 something, 2.02, 2.03. So now if you ask me, I have now a mean, that's my mean, right? I want a mean and I want an upper bound of confidence interval, and I want a lower bound of confidence interval. So this essentially, the upper bound is this plus this. So this is 121, which makes sense. So if I want the lower bound, I do this minus this. Gets me to 117 something. Good. If I want to show this now, I'm not rounding this because it's nicer to round it. Round this to 1. This to 1. Okay. So if you ask me, you want to present this, I want to have, with one look, I want to have the mean, and I want to have the range, I want to have the interval. And the way I would report this to journals is usually with the concatenate function. So I'm exporting this directly from R, and I get the same with concatenate, where I like, okay, so this is this. Then you can make an apostrophe, make a bracket. You say, okay, this is 9. 95% CI. Make a space, make a comma, and tell it this. Then you say quotation mark again, you say 2, another quotation mark. Then I say this. You can make a comma, another quotation mark, bracket closed, bracket closed. Oh, oh, that was not that. No. No. G7, this, okay. So, and this is in my head the most elegant way to depict 95% confidence intervals. You have with one look, you have here the mean. Everybody who knows 95% CI knows that the CI is always reported with a mean. You have the mean, you have the lower bound first. So that 7 and 6. Okay. You have lower bound and upper bound, and you're depicting with one look, you're depicting mean and lower bound, upper bound. So this is the most elegant way to depict this data, in my mind. Not like this. But yeah, it's an alternative way. I just think it's more convenient to do it that way. So, and you can do these calculations in the very same fashion for both. Here you see the effect of quadrupling the sample size. So if these 309 babies now overnight become 1236, you essentially have smaller confidence intervals, which is good because larger sample size, smaller variability, more accurate estimate, confidence interval is smaller. Good. Any questions to that? If not, then let's talk about beer. So, okay, good. So the following question. So a student's t-distribution. One of the most central inventions, essentially in statistics, actually was based on beer. So the t-distribution is essentially a way to estimate variability in a population from a sample. And so now this is a big thing, right? When you want to quantify variability in a population, what would you need to do? You need to measure the entire population. This is for obvious reasons not really possible. So for that very reason, you can in the set distribution, you either use a very large sample of like a size of greater than 500. So if you do quality control of 500 beers in various batches of beer, this is a lot of sampling. So we don't want to do that. Yeah, I see the smiles. Yeah, that's the logical implication of what I just said. So you want to keep that smaller, right? So for that very reason, William Gossett, who actually was the head brewer of Guinness, came up with the t-distribution. And this is where beer actually brought something really good to the statistics, because the t-distribution allows to estimate a standard deviation in quality, in an estimated quality for a population, which are like all the beers, that's the daily output of beers from Guinness, which is like, I don't know, 10,000s of bottles of beers. And you can estimate the variability of the quality of your different batches based on small samples that you pull out and test for quality. So the sampling variability in small batches is unfortunately greater, which is a problem. But this is not because of the beer, but because of the small n. So you need to do something about the n. You need to do something about the sample size. And what you do about the sample size is you assume first of all, for the t-statistics, you're basically treating it in the same way as the set statistics. So it's the same story, right? It's like it's an x minus a mu so it's an x bar minus a mu divided by the sigma divided by the square root of the n. So it's again, it's the same hypothesis testing process that we had with the set statistics. You're doing the same story here with just the estimated standard deviation. But the difference is that, so it's entirely the same kind of dynamic. So you're relating the standard error of the mean to the standard deviation, but this time it's the estimated standard deviation. It's not the actual population standard deviation. But what is different is that the t distribution is now not using the sample size for the estimation of the standard deviation, but uses a t distribution with n-1 degree of freedom. And I want to show you exactly what that actually means. But this is not as good. I want to show you one particular graph. I have that with my undergrads. I don't know. Let me find this graph quickly. Because that's very central and it makes it very, very obvious what I'm talking about. And this is, it's 13. Let's copy that as well. That's the value session. Yeah. Okay. This is the graph that I wanted to show you. And this is what I show my undergrads, and this is how I'm explaining it to them. So the t distribution essentially means to equate a smaller sample in a way to the normal distribution. So essentially what happens here, it becomes flatter, smaller, and wider. Because the variability is wide, because the sample size is small, variability gets wide, the mean is probably somewhat off, but essentially it's also smaller because of the smaller sample size. So now what happens is that this S is now essentially estimated. So this S is estimated and corrected. It's corrected for the sample size, because you have here, this is the calculation of the standard deviation in the population. You basically you build the deviations, you square the deviations, you get the sum of squares, you divide it by the n, and you make the square root, you get the standard deviation. Here you are dividing it rather than by the n, like in the standard deviation, you're dividing it by the degrees of freedom, which is n-1. And that makes a difference in the greater picture, which basically equates your sample statistics closer to the population dynamic. So the higher the degrees of freedom, the narrower the spread. So the degrees of freedom basically narrow the spread down because they're dividing and they're smaller-ing the variance. Yeah. So the larger the degrees of freedom, the t distribution approaches the standard normal distribution. So it's wider because of the smaller sample size. That you narrow it down, you get a smaller variance, it gets closer to the normal distribution. The t-square tables, which we don't need because we're using R, essentially look in the same way. So you would read it, you read here the p-values, which essentially is the amount of probability to your tail in your tails. So if you want a 5% probability, you look here. That's 2 tails, 2.5 here, 2.5 here. That's here one tail test at 0.025, 2 tail test at 0.05, and you read your t-score from here. And the t-score is calculated just like the set, x bar minus mu divided by the estimated standard deviation divided by the square root of n. I know this is a little much, but it will get very easy when you apply it, because now suddenly you don't need to worry about population means, and you can basically move ahead with your t-scores. So degrees of freedom is the number of independent observations used to calculate the statistics minus the number of parameters. And this is important to keep in mind. So degrees of freedom are different than the sample size. And they are different because they subtract for each parameter that you have 1. That means if you have one group for which you calculate a t-score, you subtract 1 from your sample size. Alternative definition is knowing the value of the statistic. Degrees of freedom is the sample size minus the number of observations that could be lost and could be recovered. Meaning if you have the statistic, if you have, let's say you have the standard deviation, you know the sample size, you know the deviations except for 1, you can essentially reconstruct that one standard deviation if you drop it. So that's the definition of degree of freedom. So the t-distribution is used in various contexts, not only for beer. So you basically can use it for confidence interval testing. You can use it for hypothesis testing, which we will do when we compare groups, when we compare before-after conditions. We will use it for various examples. Assumptions are an approximate normal distribution, which is one of the problems in many cases. So that's why it's also important that you always do descriptive statistics and you always kind of map out how your data looks like. So this is where the histogram comes into place. And that the data comes from a statistically random sample and is statistically independent. All of these observations need to be independent. So it's not that you have 3 observations from Mr. Smith and 4 observations of Mr. Miller. And so it needs to be substantially independent, conceptually independent, and from the research question independent. The robustness, they assume a normally distributed population. Real populations are rarely exactly normal. Two-sided T procedures are robust against non-normality, except when you have strong skewness. This is when you need to revisit a particular small sample sizes. Usually everything greater than 30, you're kind of safe. As soon as the sample size gets over 30, you don't really have to worry about it. So normal distribution in a sample of 100,000 patients, not really a problem. T procedures are also conservative. P-values and confidence interval will increase when the normal assumption is violated. And this is an interesting one. So, and I'm flagging this because I have myself heard of reviewers' comments. So sometimes reviewers, particularly in my world and medical world, like reviewers are statistically not as robust. And so one of the things, a friend of mine actually got a comment from a reviewer. The reviewer asked him, so he did a T statistic on a sample, on a small sample. And that sample was not normally distributed. So yeah, the probability for TAP2 error skyrockets is higher. So it's likely that he misses a difference that he should not have missed. And he claims that there was a significant difference with his T statistic. What was interesting was that the reviewer, for some interesting reason, was convinced that it's only the right thing to do when you have normally distributed data to use a t-test, and would go into the realm of non-parametric statistics. Asked him to do a Wilcoxon rank test, which is one way for non-parametric statistics, which replaces a t-test, kind of substitutes for a t-test in non-normally distributed samples, in non-parametric samples. And this reviewer did not know this rule. Because if you see a significant difference for a t-test, there's absolutely no reason why you would repeat that with a non-parametric test, because essentially p-values and confidence intervals are always increased for T statistics. And I'm flagging this because that's something that may be interesting for you. even if you never do statistics anymore, but you read a research paper, or you read a report, or you read, I don't know, an FDA submission, whatsoever, and there's something statistical in there, these are the little things that are interesting for you. And this is why I think this, telling you all of this is important, because you may not do statistics ever anymore, but you will, depending on where you go, you may be exposed to statistics indirectly, and this knowledge actually could be very, very useful to you. Yeah, one-sided tests. If somebody gives you a one-sided test, read it twice and talk to a statistician whether this is actually indicated. It's a rarity that one-sided tests are being used, so don't do much about this. Yeah, this is the robustness, and this is what I talked about before. Everything greater than 30, you're fine. Even if you have skewed distributions, run with it. Run with the statistic. Use histograms, stem plots, or box plot, investigate the properties of data. Personally, if you ask me, I would go with the histogram, but both all these three are okay. Box plot, I'm not sure I would do a box plot, because box plot to some extent, it kind of conceals the individual data point from you. It shows you the outliers, that's an advantage, but you also see it on the histogram. Personally, I would go for a histogram. But again, a lot is always a preference, right? When I talk about the confidence interval, it's like the report that the reporting that was shown earlier is not wrong. I'm not saying it's wrong. It's just it's a preference, right? It's a preference where I see advantages, and personally, I also prefer histograms over box plots. Box plots are good for group comparisons. Histograms are good for individual data and individual variables. So Q&A for t-distribution when estimating standard deviation. Okay, when we estimate the standard deviation from the sample instead of knowing it from the population, do we use the t-distribution, yes or no? Yes. The set statistic we use where we have the standard deviation from the population. Okay, the 95% confidence interval is larger or smaller when using the t-distribution than when using the set. Ah, that's a tricky one. It's wider. That's why I'm dividing it by the -1, and that's so this is a problem. But only when the n increases greater than 30, but not even then. The t-based CI becomes more similar than the set-based CI. Yes, that's true. Okay, okay. In summary, and then we're already at the end, and it's 6:30. That's actually good time. CI is given interval likely to contain the true population mean, right? So you have the population mean, you try to get samples going that basically are close to the population mean. High confidence requires a large margin of error. Yes, the margin of error increases and gives you more confidence. Your best point estimate from a sample is at the middle of the CI. Yes. Standard error and the CI tell you nothing about variability in the population, only the uncertainty in your estimate of its mean. And this is important. It's not a population parameter. It's not a Markov variability. It is an indirect, it's related to the variability in the population, but it is actually an estimate for the variability of the sampling distribution of means. And the t-distribution is used for small samples. And these are the take-home messages from today's lecture. All right, any questions on any of this? It is important, trust me and believe me, it is important, and I hope that this will come handy. I have a feeling it will come handy at one point, because I would be surprised that you go into biotechnology management and you're never going to have an assessment, any statistic in front of you. And whatever you can say about that statistics, or you can shine bright by actually knowing something that the guy next to you doesn't know, it comes handy. Statistics do come handy, just on that one. Okay, good. Any questions? If not, then we can get started with the graded lab. More or less, you get started with the graded lab. I'm just going to be hanging up there. I am around for questions, but you can get started with the graded lab. If you have any questions on anything, let me know. It would have been much nicer to do it in class, because then it's easier to kind of hang out. But I will stay on until 7. And I will also be, in case there's some specific questions, please write to the discussion board. Write to the discussion board, ask questions. I will subscribe to the discussion board. I will make sure that I'm monitoring this. Help each other. Some of you may be better in R than others. Help each other. For those that do learn, that are not that good in R, it's sometimes better to get it explained from one of your fellow colleagues, because it comes in, maybe he or she reports things in a way that he or she also came across the same problem. So sometimes it's a different approach than I would choose. And that's a good thing in many cases as well. And for those of you that are better in R programming already, you have only really understood and learned a topic once you have taught it to somebody else. Just remember them as well. Okay, now, but it makes a lot of sense. Help each other on the discussion board. I will be monitoring the discussion board. I'm happy to come on one-on-ones. If there's a problem, let me know. Okay, good luck on the graded lab. Let me know, chat to me, or just go off mute. And let me know if something you want me to explain.
I actually have to run, Professor, but thank you so much for the class. Yeah.
Yeah. All right. Good luck.
All right.
That's good.
Thank you, Professor.
I'm going to stop recording now.